Have you ever looked up at the night sky? Of course you have. You've seen the stars. They seem to shimmer and dance, a gentle, beautiful twinkle. It's a sight that has inspired poets and dreamers for thousands of years. We sing songs about it, and we make wishes upon these twinkling lights. For most of human history, that gentle flicker was simply part of their magic, a mysterious property of the stars themselves. But what if I told you that this twinkling, this romantic shimmer, is actually a problem? A very big problem for anyone trying to get a clear look at the universe. It's a cosmic deception, a trick played on us by our own planet. The stars themselves don't actually twinkle. Out in the vast cold emptiness of space, starlight is steady. It travels for light years, sometimes millions of light years, in a perfectly straight, unwavering beam. But then, in the very last fraction of a second of its long journey, something gets in the way. That something is Earth's atmosphere. Our air, the very thing that gives us life, acts like a turbulent, shimmering lens. It bends and distorts the starlight, making the star appear to jump around and change in brightness. This twinkling isn't just a minor inconvenience for astronomers, it's their greatest challenge. Imagine you are trying to read a book, but the page is underwater in a swimming pool. The words would ripple and warp. You might make out a few letters, but the full sentences, the story, would be lost. This is exactly what astronomers face when they use powerful telescopes on the ground. The atmosphere is their swimming pool. Imagine you are looking at your reflection in a funhouse mirror. Your face is stretched and distorted. But what if you could build an anti-funhouse mirror? A mirror that has the exact opposite distortions. If you looked at your reflection in the first mirror through the second one, the distortions would cancel out, and your face would look normal again. This is the core idea behind adaptive optics. This revolutionary technology aims to do exactly that for starlight. It measures the exact way the atmosphere is distorting the light from a star, and then it uses a special deformable mirror to create an equal and opposite distortion. This special mirror can change its shape hundreds or even thousands of times per second. It flattens out the wrinkled, distorted wavefront of light coming from space. The result is that the telescope's camera sees a corrected, sharp image, as if the atmosphere wasn't there at all. The first part is the wavefront sensor. This is the part of the system that sees the twinkle. It's a special kind of camera that measures the distortions in the starlight caused by the atmosphere. It breaks the incoming light from a single reference star into many smaller parts and analyzes how each part has been bent or delayed. From this, it builds a detailed real-time map of the atmospheric turbulence. This is the job of the second component, the deformable mirror. Its surface is controlled by a grid of tiny, piston-like actuators on its back. A powerful computer takes the distortion map from the wavefront sensor and uses it to calculate the precise anti-distortion shape needed to cancel out the blur. This whole process has to happen incredibly fast. The adaptive optics system must measure the distortion, calculate the correction, and reshape the mirror all within a few milliseconds. But there's one more clever trick. What if you want to look at a part of the sky where there isn't a bright star nearby to use as a reference? Astronomers have a brilliant solution for this. They create their own star. One of the most profound mysteries in modern astronomy lies hidden at the very center of our own galaxy, the Milky Way. In the late 1990s, two independent teams of astronomers began using AO systems on the largest telescopes in the world to stare into the galactic heart. What they found was astonishing. They could see the stars whipping around a central unseen point at incredible speeds, some traveling at several thousand kilometers per second. In 2008, this technique led to a historic breakthrough. Astronomers using the Keck and Gemini observatories in Hawaii used adaptive optics to capture the first ever direct images of a multi-planet system around a normal star. Not only can we see them, but by analyzing the faint light that is collected, we can begin to study their atmospheres, looking for the chemical signatures of clouds, water, or methane. Using adaptive optics, astronomers were able to watch as two massive waves of lava, triggered by the overturning crust of the lake, spread out across its surface at a speed of about 1 kilometer per day. For much of the late 20th century, there was one undisputed champion of cosmic clarity, the Space Telescope. Placing a telescope in the cold, stable vacuum of space completely eliminates the issue of atmospheric blurring. Up there is no twinkle, no seeing, no air to distort the starlight. The images returned by Hubble were, and still are, simply breathtaking. They were sharper and deeper than anything that had come before, revealing a universe of exquisite detail. While space telescopes offer a perfect view, ground-based observatories have a huge advantage in one crucial area: size. On Earth, we can build telescopes with mirrors far larger than anything we can currently launch into orbit. A 40-meter telescope has a light-collecting area almost 40 times greater than JWST. It's like comparing a small pond to a great lake. And this is where adaptive optics becomes the great equalizer. By correcting for the atmospheric blur, AO systems allow these giant mirrors to achieve a resolution that is not just as good as Hubble's, but in some cases, significantly better. Around the world, a new class of observatory is being built, so large they almost defy belief. These are the extremely large telescopes, or ELTs. With primary mirrors ranging from 25 to nearly 40 meters in diameter, they represent a jump in scale as significant as Galileo's first telescope was to the human eye. Adaptive optics is not just an add-on for the ELTs, it is woven into their very design. From day one, they are being built to work hand in glove with the most advanced AO systems ever conceived. We will be able to watch planets forming in real time around distant stars. We will be able to measure the atmospheres of Earth-sized exoplanets, searching for the chemical fingerprints of life. We will see the very first galaxies to form after the Big Bang, witnessing the moment the cosmic dawn broke. This will give us a complete picture of these cataclysmic events, combining gravitational and light-based astronomy to unlock the secrets of extreme physics in the universe. We began our journey with a simple poetic observation, the twinkling of the stars. For millennia, that gentle shimmer was a symbol of the heavens' mystery and distance, a beautiful quirk of the night sky. But we have learned that this twinkle is a deception, a distortion created by our own planet's life-giving air. It is a veil that has blurred our vision, hiding the true, sharp nature of the cosmos. But human ingenuity has found a way to part that veil. The story of adaptive optics is a testament to our relentless drive to see more clearly and understand more deeply. The discoveries enabled by this clear new vision have been profound. We have stared into the monstrous heart of our own galaxy and proved the existence of a supermassive black hole. As we look to the future with a new generation of colossal telescopes rising on mountaintops, adaptive optics will be more crucial than ever. We have learned to untwinkle the stars, and in doing so, we have not just improved our vision. We have deepened our connection to the cosmos. Our window to the universe is no longer blurry. It is wide open, and the view is magnificent.